a polynomial is a function with more than one term. That term can have constants, meaning no variables at all, or they could have variables, but we're looking for any equation that has more than one term. Now, not all polynomials have the same properties, and that's because on the variables of some of the terms in that expression, you can have what we call different degrees. And a degree is the level of exponent on one of the terms. Now, if the polynomial does not have any variables, then we say that it has an overall degree of 0. Other than that, whatever the highest exponent is in your polynomial, that is the degree that we say the polynomial is at. And depending on the degree, that is really going to influence the properties that your polynomial equation has. Now let's say we're asked to define the degree of each of these polynomials. If I look at the first one in A, I have 3x plus 2. So here are the two terms. 3x is one term and plus 2 is the other term. That makes it a polynomial. And I want to know what the degree is. Well, here, because I have no variable, this has a degree of 0. So we're going to write 0. And then this has one x term with an invisible 1 over here, which has a degree of 1. So although each term has a different degree, we look at the highest degree of all the terms in a polynomial, and that's the degree that we decide or we assign to the entire polynomial. In this case, we're going to say that this has a degree of 1. And the same is going to be true for the rest of them. So for example, this one has 0 degree, this one has a degree of 2. So we're going to write that this polynomial, or y is equal to 3x squared plus 2, is to the degree of 2, or the second degree. And then finally this one, or I have a third degree, a second degree, and then a first degree over here. What's the degree of this polynomial? Well, this polynomial is going to be to the third degree, and that's because the highest degree is 3. So let's say we're asked for the leading coefficients in each polynomial. Well, when we're asking for the leading coefficient, we're just looking for the, we could say the constant or the number in front. So I'm going to write constant slash number in front of the largest exponent, or the term with the highest degree. And then we pretty much just ignore the rest. So in this case, if I'm looking at A, then for A, the leading coefficient is 3 because the highest degree is 1, and that would belong to the x over here. And the number in front of that is the 3, so it would be 3. Now, if I look at B, the highest degree, or the term with the highest degree, is a degree of 2. And once again, the 3 is the coefficient in front of it. So it would also be the leading coefficient of 3. I'm simply ignoring all the rest here. They're not the higher degree. Now, if I look at C, again, since the degree of 3 over here is the highest degree, I'm going to ignore these. Not that they don't have coefficients. Of course, they got a number in front of the variable. But I'm ignoring them because it's not going to be the leading coefficient. So the leading coefficient belongs to the leading degree. In this case, that would be a -1, pertaining to this negative over here. So the way we can help identify what the properties are of these functions is to graph them. So if we graph y is equal to 3, we're going to go and find 1, 2, 3, and we're going to make a straight horizontal line like that that crosses through the y-axis of 3. And then we're going to graph, and I'll do this one in highlighter just because it's going to be kind of hard to see. So y is equal to 0. So we're going to go right to the 0 line and graph that. And then y is equal to -2. We're going to go to -2, so 1, -2, and then a horizontal line that goes this way. Okay. Now, there is no limit horizontally to where each of these lines would go. So what I'm going to do is I'm going to draw, we could say arrows, in order to indicate that, you would just have a constant term no matter what the x is. So let's look at y is equal to 3 and describe the domain, the range, and something that we call end behaviors. The domain pertains to all the x values, right? Or the limitations to the x values that are present in this function. Now, since we can see over here that there are arrows pointing in both the negative and positive directions, we can say that the domain or the x values range from -infinity to positive infinity. And I would label it like this on the graph. This is -infinity because it goes infinitely in the negative direction, and this is positive infinity because it goes infinitely in the positive direction. Now, when we're writing these properties in the domain, you can express it in two ways. The first way is something called interval notation. And for this notation, we're just going to use round brackets and write -infinity, comma, positive infinity, because it ranges from -infinity, right, to positive infinity. And the round brackets just mean that these are not included points, meaning that you don't have an actual point of infinity on this graph. That's impossible. So we put round brackets to tell us that these points are not included directly. Then we have something called set builder notation, where we write that the set of x, so these little squiggly brackets mean set of. It's the short form in mathematics for writing the set of. So the set of x, and when we write x here, we're talking about all x, such that, in this case, since x goes from -infinity to positive infinity, there really is no specific value that we state, or it doesn't really start and stop anywhere. So we're going to write such that x is all real numbers. And then we close this set here, and this just means all real numbers. XER is all real numbers, and that's another way of saying infinity. And in this case, it goes from positive infinity to negative infinity. Now for the range of y is equal to 3, we're going to do something similar. We're going to write that the set of all y values, and in this case, it only has one value, right? It's only 3, so we're just going to write y equals 3. So the set of all y values such that y is equal to 3. And that's the range. So you have set builder notation and interval notation. Now this isn't set builder, so we're describing sets with those little squiggly brackets. That's why it's called set builder notation. And if we were to do interval notation, well, there is no interval. It would just look like this. You would just write interval notation would just be y is equal to 3. Now I want you to pause the video and give the other two domain and ranges for y is equal to 0 and as well y is equal to -2 and write it in set builder notation. So let's say we're talking about first degree polynomials. Well, the first thing to note is that they always take the form of y is equal to mx plus b, or the slope intercept form. And the m, or the slope, is what we call the leading coefficient because it's next to the highest degree, which would be the x. The b over here is just your constant, and that would tell you where it is intersecting with the y. In terms of what they look like, if the leading coefficient is positive, then you got a line that climbs up. So this would be a positive m value. And then if your leading coefficient is negative, then it will go down. And so over here in red, we have a negative leading coefficient, or m value. Now, another thing about these is that they'll always have one x-intercept and one y-intercept whenever we continue any of these lines. Now, if we're describing the properties of domain and range, I want you to think about extending this line essentially forever. And we could do that with both of them here. And I'm just highlighting these lines and extending them. Well, we could see that if we continue the trends of either one, right, there is no real stop to the x or y values. When we're writing this in interval notation, basically, if I was writing interval notation, we could see that, well, both of them go from negative infinity to positive infinity. And this would be interval notation, but if I'm writing it in set builder, it would be to the set of all x values such that x is equal to all real numbers. Okay, and that would be for no matter which leading coefficient I'm referring to, a positive or negative one. So these properties can apply to all first degree polynomials. Now, if I look at the ranges, the same thing, where for each of them, they all slide both into the positive quadrants and the negative quadrants and kind of endlessly do so. So same thing, we're going to write open brackets for the interval notation, negative infinity to positive infinity. And we're using open brackets because infinity isn't an actual point on the graph. Now, if it was a point on the graph, remember, we would use the square brackets like that. And then if I'm writing it into set builder notation, we go to the set of all y values such that y is equal to all real numbers. And again, this is the constant properties for all first degree polynomials. So x and y, domain and range, are always x is all real numbers and y is all real numbers. The last property we can describe when it comes to first degree polynomials is something called end behaviors. And when we're describing end behaviors, what we're really doing is describing when x is increasing or moving to the right, what is y doing? Is it increasing or decreasing? And so when I look at these graphs, it really depends on what the leading coefficient is doing. So when we look at the leading coefficient that is positive, or this graph over here, we can see that, and I'll write if this is a positive leading coefficient. Okay, coefficient. Then we can say that as x increases, y increases as well. So y continues to rise positively. So it has a positive end behavior. And lastly, if we have a negative leading coefficient or a negative slope, we can see that as you move, so this would be the orange line over here, as you move more towards the right, you can see that your y value is actually decreasing. So we would say that as x increases, y decreases. So all you got to really do is look at the slope to describe the end behaviors. So the last one that we're going to talk about in this video are something called second degree polynomials, and these are essentially parabolas, right? And if you remember, they have the general shape of kind of a curved V or a thin U. And so the leading coefficient, and remember that belongs to the constant in front of the highest degree term, determines the direction of opening. And what we mean by that is the following. If the leading coefficient is positive, it's going to open upwards or kind of resemble a smile, as outlined in red over here. And if it opens downwards or presents to us a frown, kind of like this green over here, then it means it has a negative leading coefficient. Now, in terms of a maximum and a minimum value, these polynomials also have minimum and maximums depending on whether they open up or open down. If I look at this dot over here, I can see that this graph has a minimum y value. And so what we can say is that any time the graph opens up, it's going to have a minimum value. At the same time, we can see that this graph over here has a maximum y value. And so what we can understand is that if the graph has a negative, or sorry, if the equation has a negative leading coefficient, then it has a max y value. Now, identifying whether the graph has a minimum or maximum value is going to help us narrow down what the range is, because if the graph opens up, the range is always going to be as follows, where the y value is greater than or equal to the min value. And if the function opens downwards, or it has a negative leading coefficient, then the y value is going to be less than or equal to the max. Or I should say the range is going to be less than or equal to the max value, whatever that value would be. The domain, whether it opens up or opens down, is always going to be x is all real numbers or approaches negative and positive infinity. And that's because, again, remember, if we extrapolate these and keep them going in both directions as the arrows indicate, it tends to get wider and wider. Although by small increments, it still does get wider and wider. So we can say that x is all real numbers when it comes to parabolas. Now, regardless of whether the function opens up or opens down, we're going to always generally have at least one y-intercept when we extend the lines in either direction, and we're going to have two x-intercepts. And these x-intercepts have more than just one name, like x-intercepts. They're also called the roots, the zeros, and in most common cases, they're also called the solutions. Okay, so if a question asks you for the zeros, roots, solutions, or x-intercepts, they're really all the same thing. So we're looking at two x-intercepts and one y-intercept when it comes to parabolas.